So what we'll be talking about is granular media filtration. We'll look at media characteristics. We'll look at some theory. When we're looking at removing particulates, there's 5 different mechanisms that we can discuss and consider. One is mechanical screening, and this is what essentially happens in your slow sound filter. You have your particulates and your media, and the particulate is too big to fit through the pore space. And you can see this would happen on a slow sound filter, and then you would get this Schmutzdecke forming on the top of your media. Same thing happens when we talk about these mud balls. So if you get enough of these together here, then you form this kind of clump of material that is difficult to remove. We also talk about sedimentation. Here, the mass of the particle and the diameter of the particles are large enough that the particle actually settles. So this is moving by settling, and it settles, deposits on a particle. So you can see it's smaller than the pore space, but it deposits on that particle and it's removed by settling. Then we also have what we refer to as flocculation. So here, what happens, look, we've got this particle and this particle. These streamlines of the particles cause these two particles to collide with one another. They're able to attract, they're able to flocculate. And then that larger particle could be removed by sedimentation, or it could be removed by interception. So interception means, here's my particle. What happens here is the particle's moving down, my streamline, the water has to bend around the particle, and it just comes in close enough contact with my particle that it's able to attach. Impaction, my particle deviates from the flow path. So here, the particle is deviating from the flow path. Interception, it's flowing with the flow path. That's really the big difference between those two. In all cases, you need a collision to occur, and you need attachment. So in order to get removal, we need both of those happening. Now, we can also get detachment. In order for the removal to be significant, attachment has to be greater than detachment. This table gives you a sense of the physical properties of the filter media, and it's broken down by the different types of material. So we have anthracite coal, we have GAC, which is granular activated carbon. As I mentioned, this is a sorption process. It's used for sorption, not for physical removal by filtration. Garnet, ilmenite, and sand. Now, it's a number of parameters we use. One is the effective size. The effective size is defined as the sieve size for which 10% of the sand passes. So think back at the video we watched with particle size distributions and sieve analysis. So it's the diameter or the mesh size for which 10%, and it's a cumulative, 10% of the sand passes. This controls head loss. The uniformity coefficient, refer to it as UC, is equal to D60 divided by D10. So D60, it's the sieve size for which 60%, and it's a cumulative, 60% of those particles are removed, divided by T10 is our uniformity coefficient. This table from the textbook provides you with a number of values. On the other hand, the GLUM standards are slightly different. So I'm going to cross this out and I'm going to give you the GLUM standards. Quite a narrow range for the effective size. This is in millimeters. For the uniformity coefficient, according to the GLUM standards, this should be less than or equal to 1.65. Hardness, this is the Mo hardness. It is not the hardness that we talked about. It is not sum of polyvalent cations. So what's the Mo hardness? Which is easier to make a scrape into? Limestone or diamond? It's essentially the resistance to limestone, okay? So Mo hardness is a resistance to fracturing. It's how easy it is to put a scrape into that material. The lower the hardness, the more likely during backwashing your media breaks apart, and you don't want the media breaking apart during backwashing. The specific gravity is obvious what it is. The specific gravity, for instance, for anthracite coal is greater than 1.4 for the GLUM standards. And then sphericity is essentially how spherical it is. So sand 0.7 to 80%, compared to a sphere, it's roughly 75%. Essentially. One mention I want to with the GLUM standards. I posted the 2012 GLUM standards last night. It's in the design project folder on LonCappa. I was hoping to post the 2018. I had to purchase that. It's about $13. And when I got it, it said that I'm not allowed to distribute it. My plan was to originally put it on LonCappa, but I didn't for that reason. The GLUM standards are perfectly, 2012 GLUM standards are fine. As I go through it, if I see any differences, I'll let you know. But you can just design based on the 2012 GLUM standards. Last thing that I haven't mentioned is porosity. And the porosity is the volume of the voids divided by the total volume. So that's the porosity. There are a number of equations that are used to relate head loss to the various different parameters that we measure. This is just one of them. Number of things I'll mention. I'm not going to go into this in any great detail, but I want to mention a few things. One, as the approach velocity, also referred to as a filtration rate, face velocity, loading rate, as this increases, your head loss increases. And notice, because the approach velocity term is squared, small changes in the approach velocity greatly impact your head loss. As we increase the depth, we also increase head loss. As we increase the grain size, of the media, the head loss decreases. So the bigger the media, the lower the head loss. As we increase porosity, we decrease head loss. So, and small change, because this is to the fourth power, small changes in head loss, small changes in the porosity will have a large impact on head loss. I'm going to stop there. Okay, so let's then move back to the lecture. And we've been talking about filtration. Now, as I mentioned, much of what we do with filtration is really dependent on hydraulics. The whole design of filtration systems is based on hydraulics. We'll use very little chemistry. Well, we won't use any chemistry in what we do in terms of design here. So what we'll do is we can adjust the surface velocity or the approach velocity by changing the surface area. Now, once we design and construct the filter box, that surface area is fixed, and there's nothing we can do in terms of changing that. In terms of the hydraulics, we'll make a number of assumptions. And one is we'll assume that the porosity is uniform. So for a particular media, so for instance, for sand, we'll assume that the porosity of the sand is uniform throughout the depth of the bed. On the other hand, the grain size distribution will vary. And the range in porosity is relatively small, from about 0.45 to 0.55 is what we want for sand and also anthracite. The viscosity on the other hand is a function of the water temperature. So as the temperature increases, so as temperature increases, viscosity decreases. And that's important. This will affect the Reynolds number. And we'll use the Reynolds number throughout our design. Now, head loss is extremely critical. I mentioned on Monday that there were two parameters that affect when we backwash a filter. Does anybody remember what they were? So how do we decide when to backwash the filter?
One of them was head loss.
Head loss. So if the head loss is too great, we backwash. And what was the other? It's turbidity. So if the effluent turbidity is too high, then we backwash. So those are the two parameters that we monitor, and we monitor continuously in order to determine when to backwash the filter. So the head loss is proportional to the square of the filtration rate or the approach velocity. So small changes in your approach velocity or small changes in your loading will be amplified in terms of the head loss. It's inversely proportional to the diameter of the grain size. So if you decrease the grain size, what happens to head loss? I decrease the grain size, what happens to my head loss? It increases, exactly. It's proportional to the depth of the filter. So if I increase my depth, what happens to the head loss? It increases. Now, let's think about turbidity. So this is essentially removal efficiency. If I decrease my grain size, what happens to the turbidity in the effluent? So if smaller media size, how does that affect turbidity in my effluent? Okay, just think about this. If I have really small particles versus really big particles, so these are my media, and I have water flowing, which one is going to produce a better quality effluent? Or just think the smaller one. So if I decrease my grain size, what happens to the turbidity of my effluent? It goes down, exactly. So I get a better removal efficiency. So if I think about that in terms of removal efficiency, my removal efficiency increases, my water quality is improved. How about with depth? If I increase the depth of my filter, we increase the head loss, but what happens to the turbidity of my effluent? So I have a deeper bed. Can I think about this here? Get this media, get all of this media here versus this media. Then you have a couple layers. Which one's going to give us a better quality effluent? You're right, it'll decrease. So the turbidity decreases, my removal efficiency increases. And that's true for both when we decrease the grain size, okay, and when we increase the depth. So notice this. What we do to decrease our head loss has the opposite effect on our turbidity. So we can decrease our head loss, but we're going to get poorer quality effluent. When we look at backwashing the filter, and if you missed lecture on Monday, go back and look and watch it, especially in terms of the video. I think in order to understand filtration, it really helps to look at the video. You've got the link to the video, so you can, if you want, just watch the whole thing. There's a number of factors that are important here. So this is the porosity of the fixed bed. So this is during normal operation. This is the porosity of the expanded bed. So this is during backwashing. And D sub E is the depth of the expanded bed. So if you think about this, this is our filter, this is our sand. We have the wash troughs above it. And during backwashing, what we will do is we have water flowing in the opposite direction. We will expand this bed. So what we do is we'll fluidize the bed so that the water level is just over the top of the trough. The depth of the bed during backwashing, so this now is the sand. This is the depth of the bed during backwashing. This is the depth of the bed during operation. So this is D. So this is during operation. And this F is the mass fraction of the filter media with an expanded porosity. And you'll see when we go through the example. And this is dependent on the backwashing velocity. It's dependent on the terminal settling velocity of your particles, so size and density, and Reynolds number.